Well, hello, everyone. Thank you again for joining or returning to this session of the ACEEE Summer Study. And if you're expecting to be in panel 2, session 3 on alternate fuels, then you're in the right place. We've just heard a bit about the importance of energy efficiency and electrification and associated analytics in driving forward toward industrial decarbonization. And so I think this is going to be a great follow-up to talk about when those options are challenged and we need to begin thinking about alternate fuels. Before I start, I have a few housekeeping items. Again, we want to thank all the sponsors for making this event possible, especially DTE, who's the host sponsor. And just remember, you can click that sponsor link on the left-hand column of your page to read more about the sponsors. Also, we really want to encourage you to continue to ask questions of the panelists, so please be sure to drop those questions in the chat box along the way as you think of them. So we want to be able to collect those and ask the panelists at the end. We'll bring them all up and ask questions at the end and try to forward those on to them. You'll also find the column where you can see attendee resources as well. That will include conference proceedings, attendee lists, and an evaluation survey that we'd really like you to complete at the end of the conference. So those are just some things for you to keep up. And just a reminder, there'll be a post-panel debrief session at the end, and just please get those questions forwarded to us. With that, I'd like to introduce our first panelist. Mr. Stefan Buettner is Director of Global Strategy and Impact at the Institute for Energy Efficiency and Production, EEP, and chairs the UN ECE Task Force on Industrial Energy Efficiency. As initiator of the Energy Efficiency Barometer of Industry, which can be found at hashtag #EEBarometer, he facilitates demand-side informed efficiency action. He also coordinates the joint activities of EEP and the Fraunhofer Institute for Manufacturing Engineering and Automation, IPA, to decarbonize industry. Mr. Buettner is working on multinational committees such as the Energy Efficiency Financial Institutions Group, EEFIG, and the UN ECE Group of Experts on Energy Efficiency, the UN ECE Task Force on Carbon Neutrality, and is former coordinator of the G20 Energy Efficiency Task Groups on Industrial Finance, on strategies to unleash energy productivity and decarbonization potentials of industry. And these areas he's delivered over 100 speeches in 30 plus countries. With that, let me turn it over to Stefan.
Thanks, Perry, and good afternoon to you. Good evening to all who are switching in from Europe. Today, I'm going to pick out one brief section of the wide topic of industrial decarbonization. And today is also a special day in that instance, because just a few hours ago, the European Commission announced their plans how to make Europe fit for 55, meaning 55% emissions reduction by the year 2030, which has a huge impact on all sectors. And not only because of that, an increasing number of companies is striving for net neutrality, but the question is how to get there. And an ideal mix, obviously, is what everybody strives for, but there's no on-shelf solution for that. It depends on the priorities that companies have set themselves, on the situation they are in, on their motivation, and also on their deadline by which they want to achieve that. And for that, it's very important to figure out what determinants play a role and how they weigh against each other. So which mix is it, and it should be ideal for what? Because there is a very, very easy misunderstanding of terminology. I just covered this very briefly. For example, last year in October, Japan got a new government, and the New York Times reported that this new government wants to lead Japan to carbon neutrality by 2050. Other sources say, okay, Japan wants to become climate neutral. Sounds similar, it's not the same. And that misunderstanding happens frequently within companies, within governments, within the media, within the general public, everywhere. So, and that misunderstanding is understandable just because the unit within which we measure greenhouse gases is CO2 equivalent. So, and therefore, getting a common understanding of the terminology is crucial. But that aside, also, how far do we want to go? Do we want to become net zero? Do we want to become, like some companies, carbon positive? Do we want to only achieve, say, 80%? And by when? So in order to be able to shape an ideal strategy, we need to identify where are we starting from? How much emissions do we actually emit at the moment? What's our energy consumption? And where do we want to end up at? And also, very important, what is our motivation? What drives us there? And here it's advisable not to look simply on speed or how do I get there cheapest, but also to look at milestone years. For example, the German automotive supplier Bosch announced surprisingly in May 2019 that they wanted to become carbon neutral by 2020, so within an 18-month period. And they announced that they are going to spend 2 billion euros within an 11-year time span until 2030. But once they have reached 2030, it will only have cost them 1 billion because they apply a changing set of measures. There's one set to become net zero rather quickly, but then the ingredients change along the way. So the share of efficiency is increasing, the share of on-site generation is increasing, new processes are being applied everywhere, and there is a big argument why to rush. And that big argument is increasing prices. Increasing prices predominantly, and that applies for Europe at the moment, but an increasing number of countries and regions are looking at emission pricing schemes. So far, about 24% of global emissions fall under one or another of those schemes. And as we see in the blue line here, the European emissions price ETS, which is charged on very emission intensive sectors, 5 of them, as well as on electricity generation, has been rather low for a long period. It was between 5 and 10 euros for a couple of years. And until last year, October, November, when the European Commission announced their raised ambitions, it shot up and doubled within less than 6 months. And we'll see within the next couple of days whether it will shoot up even higher. So also we have national schemes that have a fixed price, which is the orange line, introduced in Germany this year, January, where we have 25 euros per ton emitted on everything that is not already charged by ETS. And that will then gradually increase first by 5 euros a year, then by 10 euros a year. But also with the upcoming general election, it's likely that this emission price is going to be even higher than forecasted. So there's, for the first time, also another incentive to look how much investment costs do I have for which measure, and have something that I can count against it, aside efficiency savings. So things pay back rather quickly. Also, when we look at the different types of interventions, for example, everything on site that needs planning permission, we need to get into the planning offices before my competitor does. Otherwise, I may have to queue up. Also, when I look at substitution of my fuel source from something that is very carbon intensive to something that is zero carbon, so typically renewables, for instance, then there are not sufficient amounts available in the grid. Also, the grid don't expand quickly enough, or cannot handle that at the moment, which means that there may be an overshoot in demand, increasing prices. So there are a number of reasons why it's difficult to find the ideal mix and to be quick enough before there is external supply shocks or price shocks. In order to find out how companies at the moment find their ideal mix of measures, we have applied a methodology consisting of 3 different components. One is in-depth interviews with the companies that we work with on a one-on-one basis to help decarbonize them. Another one is literature review, so scanning announcements from press, media, company press releases, etc., and then validate our guts feelings, our experience on the broad basis by putting out a questionnaire to about 1,000 manufacturing companies within Germany, but we'll see later on not only there. On that instance, on that question, we have reached out successfully to 864 companies, and we asked them the question, so if you want to be decarbonize, which factors are most decisive in making up your choice? Is it the level of investment that plays the biggest role? Because things can be rather pricey, and if you don't have enough investment cash on the side or difficulty getting loans, maybe that is a limiting factor. Or is it the image effects? I want to be seen as a company that moves forward boldly and therefore has lots of emphasis on things that can be seen and noticed. Or is it, how do I get it done cheapest per ton of avoided CO2 equivalent? Or maybe it's also the expected productivity increase. That's not only energy productivity, that's productivity overall. But it could also be, the more complex a production is, that technical aspects are the limiting factor or the motivating factor. How complex is, how deep does it go into my process? Are there risks to disrupt my production? Or is it simply the availability of competent personnel that can help me implement it? As we assume that the situation differs quite broadly depending on which company size we have to deal with, or how energy intense a company is, or what sector they're in, we have cross-referenced all this question against a number of different dimensions and also against the dimension of motivation. In that questionnaire, we asked lots of other decarbonization-related questions, but these are not the focus of today. And the data that we gathered in conjunction with a number of partners from within the country, including the German Energy Agency and the Federation of German Industry. As for the data sample, we span across all company sizes. So we have a nearly even distribution across the 4 sizes from micro companies, less than 10 employees, small companies, less than 50, medium, less than 250, and large ones. But also, we looked at their energy intensity, and we grouped 5 intensity classes defined as watt hours per euros. The euro is at the moment at round about $1.19 per euro, and 1 watt hour equals about 3,600 joule. The category very energy intensive drops out because later on we'll not have sufficient responses in each of the answers. Now, looking at the general result for the sample, we notice that surprisingly, there are the soft factors that are lagging tremendously behind. So at the top, we have the cost factors, the cost per avoided ton of CO2, the level of investment. Then we do have technical aspects, and then the productivity increases. Now we see 3 colors here, prio 1, 2, and 3. That is that we asked them to name their first priority, their second priority, and then the third priority. They didn't have to give us a second or third, only the first was mandatory. So, and therefore, we looked at what was the number 1 priority, and then we looked also at what was sticking out as secondary or tertiary and overall as a priority. So we see also that even though the financial aspects are going first when it comes to the first priority, we see also that productivity and technical aspects come in second place, because that's a very important thing. If it doesn't increase your productivity, should you really do it? Or also, if it's technically troublesome, would you really want to go into that? However, in overall priority, so the decisiveness, which is going to be the first three priorities added up, we see that all financial factors, technical aspects, and expected productivity increases are on the same overall level. Competence appears to be less important because nowadays you can hire that in rather easily. Looking at this from company size, and because I would otherwise have to have combined 6 or 7 charts in one slide, which would have been rather hard to digest, I only illustrate you now the top 2 listed number 1 priorities and the top 2 listed aggregate priorities. On the left-hand side, under the heading General, you see a recap on how it was on this initial slide, on the general sample. So what sticks into my eye here is that the number 1 and number 2 priorities differ depending on company size. So surprisingly, the relative avoidance costs are number 1 first priority with micro companies, even though one would assume that those would typically have a lower investment budget, therefore more difficulties in putting up the upfront cost for an intervention. And therefore, one would have thought the level of investment is the issue and not the avoidance cost as a number 1 thing. We see that there's a similarity between small companies and large companies on the right-hand side that have the same order, but we also see that there are a couple of percentage points apart from another. Technical aspects are, however, the most important determinant for quite a number of those company sizes when we look at the overall importance. So for micro companies, it's nearly half of companies. Also for the medium-sized companies, it's rather important, but we see they differ largely across the sizes. Here I pick out this implementation competence element. It's a priority for less than a quarter of companies of the micro size, perhaps because they're just used to hire in expertise because they're so tiny that having in-house expertise is just not feasible for them. Also, it may be a consequence of companies thoroughly assessing the technical aspects where too complex solutions that would require specific competencies are ruled out beforehand. We took a closer look at the dimension of energy intensity of companies. And there we would have typically those steel companies on the one hand side and very intensive companies on the other end of the spectrum. And there we see that for the non-energy intensive companies, as energy-related emissions are often the main cause of emission under the direct control, it makes sense to look at the level of investment for them a bit more, whereas the proportional share that they have of the energy cost of their total cost is relatively low. So they save a proportionally high share of energy, which doesn't have as a big effect on the total cost as it would have for more energy intensive companies. Also here we see huge differences, and not surprisingly, it's the energy intensive companies that rank technical aspects first. Imagine a steel process where you would have to change lots and lots of things to convert that to zero carbon. So for example, the traditional process to steel production with green hydrogen. Also, the overall top 1 to 3 priorities, the aggregated ones, we see that there's a repetition. Again, technical aspects are here the most important ones. Surprising. That is a category also where image effects are nearly on the same level. So that means, yes, we are the bad guys because we emit so much, and therefore, when we decarbonize, we put a high effort on the one hand side on the technical issues, but also on the image effect. Now looking at the different sectors, we classify 27 different manufacturing sectors. And here, because it is so many, we change the way we present that. On the top in orange, you see the branches or the sectors that most often ranked that category as high priority, as that number 1 priority. And in gray, you see those sectors that have the biggest aggregate share for this dimension. So the expected increase in productivity across all sectors is most often the top 1 priority in the food industry, followed by the chemical and chemical products industry. And for that sector, it also has the highest overall importance. The chemical industry is also the industry which has the largest, very large process emissions to deal with, and where the products are also rather difficile. If we look at image, pharmaceutical products and non-metallic mineral product sectors are putting the highest emphasis on image effects, not the highest within that sector, but across all the sectors, they are the ones that most often mention that as first priority. If you look at the overall priority, more than half of companies, again in the pharmaceutical industry, see that as an important factor, followed by the paper and paper product sector. When we look at the implementation competence, it's more the printing sector, and again the chemicals that are standing out with top 1 priorities. But for overall priority, it's the food and the basic metal sector. Technical aspects in the very widespread sector of other manufacturing, and we see the overall priority is over 60% for that sector as well. And the same applies to the leather and the related products. Is there a link between being a supplier or not? That is an important question. And there is a small one. Oh, that's a wrong graph, so I just switch. Here's the correct one. And that is that whilst the avoidance cost for both of them is the number 1 determinant, the level of investment is more important to those being a supplier, whereas it's more the technical aspects for those not being a supplier. And in the paper, you will see more details on that. When we look at the motivation to decarbonize, there are some surprising results. So is it customer requirements or government requirements or image? There we have a number of different dimensions, and I'm going to click through rather quickly to those. You'll get that afterwards, I assume. CSR, corporate social responsibility, plays a rather large role. However, it's surprising that there the relative avoidance costs are the highest thing and not the image. On the other hand, those companies that are motivated for decarbonization because of image, for them, the avoidance costs, so how do I get my image cheapest, is the driving force, as we can see here. That I already said. So the reduction of cost risks is an important thing, as are the long-term economic advantages. So if we summarize all that, what influences has the motivation to decarbonize? The reduction of cost risks is a very important one. Customer requirements are for the level of investment, long-term expectations, productivity increases, and CSR context for image effects. Putting that all together, there are 4 determinants that were most frequently named decisive in determining the mix, which is the relative costs, level of investment, technical aspects, and expected productivity increases. However, external factors drive that big time. It's the current economy, available financial and stimulus systems, or also the emissions price. There is no standard package to deliver that. And what also needs to be said, that is a snapshot of the situation in Germany. However, that said, we do capture that data also for other geographies. So the same questions are currently being asked in the US, in Canada, in Mexico, and many other countries. So if you're interested, just go on that link and fill in the questionnaire. Many thanks.
Okay, great, Stefan. Thank you for that interesting data on the drivers for adoption of decarbonization strategies. I'd like to move on to our next presenter. He is Richard Chandras, and he's Associate Director with the Energy, Sustainability, and Infrastructure Group of Guidehouse, which was formerly Navigant Consulting. Rich focuses on assisting clients with the technical, economic, and policy aspects of emerging technologies. His areas of focus have included sustainability, distributed energy resources, microgrids, and energy efficiency. Rich has recently been focusing on the technical issues involved in decarbonization across industry, the power and gas networks, and commercial and residential applications. Rich has 30 years of engineering, project management, research and development, and regulatory experience in industry, consulting, and government. He holds a bachelor's degree in environmental engineering and a PhD in chemical engineering. Rich, take it away.
Thank you so much, Perry, and welcome everyone. I really appreciate your time and attention. What I'm going to talk about here is decarbonized hydrogen in industrial processes, and what the challenges are, and whether that's going to be possible, and so forth. So this slide really talks about what we mean by decarbonized hydrogen. I found it a little hard to put together this talk because I'm not sure what level of familiarity folks have with respect to hydrogen at all, but this slide is really to just kind of get everybody on the same page in terms of
sorry, Richard. Excuse me, sorry, you just need to share your slides again. They're not coming up.
Oh, okay.
Thanks.
No problem. How's that? Oh, okay. I think I didn't click on the window share. Let's see how it goes now. I apologize, everybody. Can you see them now?
Yep, I can see them. You just need to press present. We should be good.
Okay.
To go. Looks good.
Sorry about that, folks. Okay, so picking up here, really, a lot of people have the impression of hydrogen, especially if they've been introduced to it by proponents for the mobility or transportation sector, that hydrogen is so clean because you burn it or react it and all you end up with is water. And that is true, but the problem is that there are emissions involved in production of hydrogen currently. The overwhelming amount of hydrogen production is by a process known as steam methane reforming, in which natural gas is used. And in the reaction part of the process, you produce hydrogen and CO2. And you also need a lot of heat energy to operate the chemical reactor. So there's a lot of combustion of natural gas, and that gives off CO2, which happens to be harder to remove as well than the CO2 from the more concentrated reaction stream. So cleaning hydrogen involves one of two different pathways. You can continue to do the same chemical reaction based on fossil fuel, natural gas, or even coal and other fossil fuels are possible. But if you do that, you would have to remove hydrogen primarily or initially from the reaction stream, and ultimately, if you're going to get up into the 90% or so, from the combustion stream as well. What there's a greater focus on now is green hydrogen, in which what you're doing is you're electrolyzing water to produce hydrogen. And ideally, you're electrolyzing it with some green electricity source so that you're not emitting a lot of carbon in producing the electricity. You can also get green hydrogen by biogas and biomass, and a future, right now it's kind of science fiction, but it will happen in the future, pathway is by artificial photosynthesis. So let's take a look at the opportunities for decarbonization that exist within industry right now. This is the US industry data reported by the manufacturing consumption survey that the Energy Information Administration does. And the blue shaded areas are electric fuel consumption, and fossil fuel is that rusty color. And you can see that there's about 60 to 63% or 62% of the entire industrial energy usage. It takes place in boilers and process heating. And much of boilers can be electrified. One of the issues, and I believe Stefan referenced this, is it would require a large increase in electrical capacity. And it's especially hard for retrofits where you would have to take a good boiler and just replace it with an electric boiler. On the process heating side, you have more of the hard to electrify kind of usage of fossil fuel. And you can divide the process heating into general application equipment such as air heaters or common types of process heating, and more specialized equipment such as kilns, special process heating that is very customized, furnaces, ovens, and so forth. That's where a lot of the non-feedstock hydrogen use that's going to take place in industry is going to happen, is in that high temperature specialized equipment that is hard to electrify. So what are all the different kinds of use cases for low carbon hydrogen in industry? Well, hydrogen is already used quite a bit in industry as a feedstock. And so if you can green it by introducing low carbon hydrogen, then that is a very good start for decarbonization. You can't electrify to replace that hydrogen, and there's no labels on the atoms and molecules saying that it's green. So essentially just greening it, it just basically just adds decarbonization without any much competing opportunities. The other major uses are as a fuel, which is not really much of a use right now, except to some extent, probably a significant extent in the petrochemical industry, but not much elsewhere. As a process atmosphere, which is really important in things like glass making and especially metals processing, or as a heat transfer medium. That's a much lower volume use. So the real opportunity is for new decarbonization and new uses of hydrogen would be as a fuel. So let's talk about molecules versus electrification. There's various pros and cons for each of them. And the first one that comes up is basically that if you're producing green hydrogen by a non-bio method, you are using electricity, and there's efficiency losses, conversion losses to get to hydrogen from the water. So the baseline case would be just to use that electricity directly as electrification, and the local efficiency is good as well. because you often have more heat losses in furnaces, ovens, kilns, boilers, and so forth. Battery, using it for energy storage, batteries are great for short-term, as in like a day or less. But when you're talking about medium or long-term, that's where hydrogen and perhaps, or probably other molecules can be, have an advantage. In terms of cost, you've got costs involved in equipment, R&D to get equipment to replace existing equipment that is not electrified right now. You've got infrastructure. You have infrastructure both for electrification, as I referenced, and also for hydrogen. We'll get into some of that. In the case of electrification, if you're in a region where the peak demand pricing is in effect, unless there's a special industrial version of that, you could have yourself a real problem with using so much electricity in that worst day of the year. In terms of compatibility with industrial processes, electrification, at least currently, generally requires low to medium temps. And that, by medium, that could be fairly high. It could be up to 700 or 800 degrees Celsius. But it's also the case where you would, with a flame or combustion, you're mixing the gases with the materials that you're heating. And the residence time of the gases with the material to get a certain amount of heating is much shorter, and you would have to have longer residence time to get the radiation and conduction from electricity. So some processes don't give you that much residence time. So hydrogen or other energy carrier molecules would be better then. And the other thing is the environment. It's easy to get fouling and issues with heat transfer on electrical heating equipment that would not necessarily be so important with combustion. And in terms of infrastructure, you're talking about potentially large equipment and feeder connections for the electrification. That is also true for electrolyzers. And if you had on-site electrolyzers, you would be losing energy in the electrolysis. So pipelines really are going to be the way to get around that, where you have the good infrastructure to begin with, you produce the hydrogen, and then you pipe it elsewhere. In the meantime, industrial clusters were a sort of local centralized source of hydrogen would come. I'm looking at the time. I'm already taking up a bunch of time here, so I'm going to not go through all of these, but there are a lot of technical issues, challenges, if you will, to getting to some of these high temperature industrial processes that that use hydrogen instead of natural gas. The reference point you should use is natural gas as opposed to electrification. And so when you compare, for example, heat transfer from a hydrogen flame versus a natural gas flame, you've got much less radiation, for example, from a hydrogen flame. And so there has to be methods to increase that or to reduce the need to transfer your heat by radiative heat. You've got a higher temperature in your flame, so NOx emissions are higher. That is an issue and something that needs to be accommodated. Possibly if you were burning pure oxygen that came off of the, if you needed really high temperatures and flame intensity, burn the oxygen, then that's not so much of a factor. The burning characteristics and combustion characteristics for hydrogen are very different than natural gas. So the burners have to be designed appropriately. The control systems and gas flow systems have to be designed appropriately. And what you're ending up with is a much wetter flue gas, which may, if there's contact with the product, that could create issues, having a much wetter gas, as well as just wetness in the combustion chamber and the exhaust gas, which can create issues there. All this is being researched for some industries and will be researched for other industries. Gas is one that, glass is one that is starting to make progress on its own volition. And safety systems. Obviously, we know hydrogen has its own safety issues that are different from natural gas, and they're important. So, producing green hydrogen via electrolysis does have energy efficiency implications, but I should point out that for thermal applications, they're less than what people currently are thinking. Part of the reason for that is because when you're thinking of the energy content of your gas, when you're talking about a combustion application, you're looking at the higher heating value as opposed to the lower heating value, which is what you're thinking about when you think of power applications. And current modern day electrolyzers can reach some pretty high efficiency. Just at the electrolysis, you can get to 93% higher heating value. Now, there's also other balance of plant like power rectification and so forth, but you may need power rectification and electrification in certain industrial processes as well. Where you're really going to get a big ding is if you need compressed hydrogen, because that can use a really significant amount of additional energy. And some of that energy you need if you're going to do pipelines. If you're going to be storing on site, you need to really compress it quite a bit, and you can lose a lot of energy. This just shows the whole hydrogen value chain, and we just wanted to point out places along the value chain where there's going to be R&D and development and scale up needed. So in the feedstock, electrolysis technology, scaling up in production to reduce costs, bio feedstocks, which are complex to deal with. Carbon capture, as I mentioned, is super important, but yet, costly, especially if you're going to try to capture all the carbon. Electrolysis, as I mentioned, in terms of efficiency and so forth. The energy costs of compression and liquefaction are not negligible. Transport, there are not too many hydrogen pipelines, only in certain places. And it's possible to do some gas blending, but that has its own issues. I'll be talking about that in a slide or two. And then the question of if you need to store it on site, if you don't have, for example, hydrogen pipelines sufficient to give you a constant stream, or if you're trying to store it a lot to have long-term storage, a lot of the above-ground storage options are not terrific. So geological storage is a question, and that needs to be a lot more research and development to be looked into for certain kinds of storage that you may not have the underground formations in your area that are known to be pretty good, but you may have some that might be good, and there needs to be further research. You can also convert hydrogen into hydrogen carriers like ammonia and liquid organic hydrocarbons, and then transport in liquid form, in which you're talking about a lot more density of energy. But you also have costs, and you have to recycle the materials and so forth. So that whole thing is another area of R&D and development. The devices involved in doing the combustion need to be developed to be compatible with hydrogen or blends. And then finally, if you're going to make industrial synthetic products, you need to, I just want to back that up. Well, I lost that. You need to get those low cost and highly efficient, and in some cases you might need them distributed to make it make most sense in terms of where the renewable energy resources are. So with all this stuff, there are some barriers, challenges, if you will. What we believe is going to happen, hydrogen is not the answer to everything. Nobody is thinking that, or very few people are thinking that. And if anybody in the audience is thinking it, really it's got its place, and that's what it is. It's going to be side by side with electrification, methanation, and energy carriers, and all sorts of other things. But in order to ameliorate some of these challenges that I've talked about, we're proposing that there's a virtuous cycle involved. And as you go around this circle more and more, the difficulties are going to get less and less. So right now, there's not a lot of demand for green hydrogen. As there's more demand, there'll be more incentivization of all parts of the value chain to get more efficient, to get more cost effective. It might be, and as Stefan mentioned, in Europe, it already is happening, that you need policy drivers and incentives such as a cost of carbon in order to be able to really get that demand up. That may be what it takes, or On the other hand, there are a lot of utilities and a lot of entities and government entities and so forth in the United States who are, with a wide eye towards the pros and cons, looking at hydrogen here in the United States. Once you have the demand, then the production advancements can get the cost down to be more reasonable. There are new initiatives in the United States to get the cost down to $1 a kilogram ultimately. And you have to get those transport pathways. That will be a big bottleneck. If you have to truck it, it's a very low density, energy density on a volumetric basis. So you need pipelines and so forth. In the meantime, there will probably be some on-site and industrial cluster production that is a starter for it. So here's the challenge with storage. Basically, on a volumetric basis, hydrogen is a light molecule. It doesn't have many kilograms per cubic meter under normal standard conditions, and so you have to really compress it to 200 bar, and then you would get 13.3 times the volume for a given energy density that you would have in diesel fuel. If you convert it to ammonia, you're only talking about 60% more than diesel, and then there's these other storage methods, liquefaction, storage, and metal hydrides, and then those conversions into other energy carriers. Because of this, for large amounts of hydrogen, we're really talking about geological storage seeming to be the most feasible avenue for the large storage. So if you're not going to store it and you need to get it to your industrial site, really, ideally, you'd want to send it via the pipelines. Just tube trucks and so forth are not going to be great except for small uses like maybe atmospheres in a small plant or something like that. Two basic options: you can blend it with natural gas into existing pipelines, or you can do something so that you can put pure hydrogen in the pipelines, either upgrade the existing pipelines or create new pipelines for pure hydrogen. Hydrogen can be blended with natural gas into existing pipelines with not much equipment modification at all, but the problem is it also has a minimal impact on decarbonization. I should also mention that you can, for those who want to get pure hydrogen on the other end, there are technologies being developed to purify it via membranes on the offtake side. So you can transport it and have it as pure hydrogen or close to pure hydrogen on the offtake side. The greater your concentration of hydrogen with natural gas, the more you need accommodations to the existing gas network. You've got compressors, some of which don't exist for large volumes. You've got, and in any case, have to be retrofit for smaller volumes. You've got to deal with leaks. It's a leakier gas because of its diffusion, embrittlement of the pipelines, different safety issues, cost, so forth, and that you have to pressurize it more because per unit volume, you're delivering less energy. In terms of existing pure hydrogen pipelines, the US right now leads the world in dedicated hydrogen pipelines with 1,600 or so miles of it. But it's almost all on the Gulf Coast in that industrial area, a little bit in California, and a little bit, I think, somewhere in the upper Midwest. And that's not going to be the case much in the future, because in Europe, the gas networks, and Guidehouse has been working with these gas networks in terms of helping to develop this vision and do analyses and produce the reports on it. In Europe, they realized that this problem with being able to get the hydrogen to the various places people are going to want to use it. So something like 25,000 miles by 2040 are envisioned with this consortium of gas network providers, both repurposed pipelines, which would be about 2/3 of the capacity, and then newly constructed ones. I think in Europe there's a lot of the smaller kind, much less so in the United States, but so the average size of the pipes are going to be increased as well. So this is a vision for the future going to 2040 and beyond. On the production side in Europe, we're talking about a lot of electrolyzer plant steel that's going in the ground over the next 5 to 10 years. We're not even talking 10 to 20 years. We're talking very quickly, like 10 million tons per year to be produced by 2030, 1 million tons of hydrogen per year by 2024. Many large projects over 100 megawatts electrical into the electrolyzer have been announced. Just in Germany and Netherlands, we're talking about a total of 87 different projects. They're not all electrolyzers, but pipeline and electrolyzer in combination, quite a few projects, big names in the chemical and utilities industry. And you can see here where all the electrolyzers going in the steel is going in the ground. Okay, and then, so let's say we talk about the capital, that you can transport it, you don't have to store it so much, or you have big salt caverns or something like that to store it, and the prices of the capital equipment for electrolysis are going to go, those prices are going to go down. But what does that mean in terms of the cost of hydrogen? Well, a really big factor is the operating cost, the cost of the electricity. And this is for a very expensive type of this chart here is how much the hydrogen cost is made up of different kinds of factors. The brown is electrical costs, and this is a very expensive type of electrolyzer that isn't that well developed. The new electrolyzers are cheaper and represent a smaller percentage of the final delivered cost. So anything that increases efficiency, anything that reduces the price of electricity, having a price on carbon, again, is probably going to be a key factor as well. There are other factors that would make hydrogen strategically better for specific sites, including the need to store energy on local sites, the need or the ability to produce synthetic chemicals with what you're making. There's a lot of things that where you can get more value out of it than just what you would get by burning it. So it's not that no hydrogen will be used at these higher prices, but we really want to get it down to much less than what it is right now. So looking at the whole virtuous cycle, what is happening when you look at the whole picture, big initiatives to reduce the price. Ideal in Los Angeles is trying to get the price of green hydrogen down to $1.50 per kilogram by 2030. A new initiative, federal Earthshot initiative, to get the price of hydrogen down to $1 a kilogram. So on the, these things will help to increase demand. There's research and development being done for large vehicles, for various industries such as glass making, even potentially cement kilns or pre-calciners in cement kiln areas, metal heat treating like crazy. So the demand work is starting and is being done on that side. And then on the transportation and production side, you've got a lot of steel going in the ground, a lot of pipes planned and so forth. So at least in Europe, we're seeing this is really going to reach a critical mass. And there's no reason to think that once things are worked out and the technologies are worked out to be really competitive with electrolysis, really cost effective and so forth, that wouldn't get transferred over to the United States. As I mentioned, some cost reduction and demand initiatives are already taking place on the United States. So the basic punchline really to the whole thing is it's not here yet. It's a piece of the puzzle, but I think people need to start taking it seriously and start paying attention really to the development within your own industry or any industry that you're concerned with. And that's basically it. I look forward to hearing your questions after all the presentations.
Okay, great. Thank you, Rich, for all of that terrific information on the opportunities and the challenges that a hydrogen or hydrogen-based decarbonization in a future economy will face. So with that, I'm going to move right ahead to our next panelist. Bruce Hedman is Managing Director of Entropy Research, LLC, and he has 40 years of experience in energy technology research, development, and commercialization, with a focus on industrial energy efficiency and combined heat and power, and distributed generation technologies, markets, and policies. He's worked extensively with public and private clients to analyze the opportunity for distributed generation technologies and identify regulatory and institutional hurdles to market development. Bruce currently serves as Senior Advisor to the U.S. Department of Energy's CHP deployment program. He has also provided technical support and strategic guidance to the U.S. Environmental Protection Agency's Combined Heat and Power Partnership, and has worked with a variety of states analyzing the opportunities for the barriers to CHP and distributed generation. I'm really looking forward to this, really curious about the role of CHP in a carbon-free future. Bruce, take it away. Thanks.
Thank you, Perry. Good afternoon, everyone. It's really a pleasure to be here on this panel and back at the Industrial Summer Study, albeit virtual. I'm going to talk about beneficial CHP. Is that a thing when you look out into the future of decarbonization? And I'm sure all of you know that combined heat and power cogeneration has long been a key efficiency tool for industrials. It saves energy costs, enhances reliability, and has been reducing both criteria pollutants and carbon emissions for facilities that use CHP. But given that the bulk of current CHP capacity uses fossil fuels, particularly natural gas, the question arises on what is the role of CHP in a decarbonizing economy. And I'm sure you also know that the plans for widespread electrification as the path to decarbonization at the state and local level have already led to policy and some consumer pushback against natural gas in some areas. So this is a pretty important topic right now. I mean, as an example, over 20 cities in California and others in the Northeast have banned natural gas in new construction. There have been regional efforts to stop investment in natural gas infrastructure, such as pipeline expansions and natural gas CHP systems individually. And this certainly has led to industrials that have long relied on CHP for reliable and efficient energy, really to question what's the long-term viability of CHP? Can it help me get to our decarbonization goals, or is it going to end up being a stranded asset? And this discussion today is our high-level look at how CHP could fit into a zero-carbon economy and help decarbonize the industrial sector. And I think this is a really perfect follow-on to Richard's discussion on hydrogen, because to a certain extent, as hydrogen goes, I think is as how the future of CHP goes. I'm going to start with our conclusion. We do think there's an important role for CHP in decarbonizing the U.S. economy and U.S. industry, particularly in providing low or net zero carbon energy services to markets and process, and Richard talked a little bit about that don't lend themselves easily to electrification. A couple things to remember. First, it's important to note that CHP is fuel flexible. Yes, 70+% of existing CHP capacity is fueled by natural gas, and that's really because of gas's historic availability, its ease of use, its lower emissions and lower price. But CHP currently also uses a significant amount of renewable fuels, low carbon waste fuels, and hydrogen where available. And CHP technologies will be ready to use higher levels of fuels such as biogas, renewable natural gas, and hydrogen in the future. And I'll talk about a little bit about that later. Secondly, CHP is the most efficient way to generate power and thermal energy, and already provides significant CO2 reductions and fuel savings today. And we believe will in the future, wherever marginal grid generation is based on a combustion technology. And whether that's fueled by natural gas, biogas, or some zero carbon fuel such as hydrogen, there will be an efficiency advantage to using CHP. We believe there's a role for renewable hydrogen fuel CHP to decarbonize thermal end uses in industrial and commercial facilities that are difficult to decarbonize, either in terms of technology or in terms of cost and expense to change out the production assets. And we believe that renewable hydrogen fueled CHP can decarbonize critical facilities that need dispatchable on-site power for long duration resilience and operational reliability, which is becoming more and more important to a lot of facilities. Finally, we believe that CHP's high efficiency can extend the supply of renewable and low carbon fuels such as hydrogen, which will be initially limited in availability and expensive. So my next 10 slides or so are really just to highlight a couple points that support these conclusions, I hope. First, I'm going to start with, to set the stage with the role of CHP in the US today. There's just shy of 81 gigawatts of existing CHP currently installed at more than 4,600 facilities. 82% of this existing CHP is in industrial applications. The 81 gigawatts represent about 7% of total US generating capacity. And we estimate currently saves about 1.7 quads of fuel and over 200 million tons of CO2 annually. That says metric tons, but that's not correct. It's million short tons. And despite the uncertainty about the future of natural gas CHP, or fossil fuel CHP, I should say, we do see growing markets for CHP in non-traditional applications where energy reliability and resilience is important. So there is quite a healthy market for CHP currently. And as I just mentioned, CHP is fuel flexible. While the bulk of current CHP capacity is fueled by natural gas, 72%, there's significant use of non-fossil fuels such as biomass, biogas, municipal and process waste, where they are available and cost effective. In fact, over the last 10 years, 25% of the installed CHP capacity over the last 10 years has been in zero carbon fuels, not fossil fuels. Just to follow up on fuel flexibility, if you look at CHP in the industrial sector, and this is a broad definition of industry, it includes manufacturing, agriculture, mining, oil and gas, water treatment, things like that. Again, currently 15% of existing industrial capacity is fueled by non-fossil fuels, such as biomass, biogas, and waste heat, driven, again, by if it's available and at a reasonable price, including cleanup. But note that this 15% of non-fossil capacity actually represents 44% of the number of existing industrial CHP installations. There's about 1,700, I believe, that are out there. So there's an enormous track record and experience base for operating CHP on renewable and other non-fossil fuels by both industrial end users and by CHP suppliers. So I think that's an important, item to remember. I mentioned earlier that CHP is the most efficient way to generate power and thermal energy. And as such, it does provide significant CO2 emissions reductions and fuel savings today. And we believe will in the future, wherever marginal grid generation is based on a combustion technology. And as I said, whether that marginal fuel is natural gas, biogas, or some carbon zero fuel such as green hydrogen. Don't worry, I'm not going to go through all the numbers here. You can review the details when the slides are posted. It'll also have my contact information. I'd be happy to discuss the details with anyone offline. But this is a pretty straight up comparison of the fuel use and CO2 emissions from a 20 megawatt industrial gas turbine system fueled by natural gas. It's sort of in cartoon fashion on the right there, compared to conventional separate heat and power, grid electricity, and an on-site natural gas boiler providing these same services. And you can see that, pictured on the left. It's based on assuming a 90% load factor and typical electric and steam output for a CHP system of this size. That's pretty typical of an industrial CHP system. The steam from CHP system displaces an 80% efficient natural gas boiler and displaces on the grid marginal grid generation, which in this particular case is estimated by using EPA's 2019 National Uniform Energy Efficiency Factor from the AVERT system, which is meant to be a first cut estimate of marginal grid emissions. You can do it either at the national basis or on a regional basis. And if you look at the black boxes, you can see that the higher overall system efficiency of CHP, 70% in providing these energy services compared to 53% for separate heat and power, results in energy savings. Really about 25% of the fuel in separate heat and power is saved by using CHP, and a 43% reduction in CO2 emissions from separate heat and power to combined heat and power using natural gas. This table just brings those energy and CO2 savings from that 20 megawatt natural gas CHP system on the previous slide, and lining up with the energy and CO2 savings from 20 megawatts of utility scale solar PV and 20 megawatts of wind capacity. And first, it's important to note that CHP, like energy efficiency projects, like renewable projects, end up displacing marginal grid generation from marginal generation resources from the grid, and that includes T&D losses as well. And today, the marginal grid generation is currently a mix of coal and natural gas in most regions of the U.S. And you can see in this chart, in this comparison, you can see the annual CO2 savings from natural gas CHP. It's that red number down in the first column, the natural gas CHP column at the bottom in red, 70,815, which is from the previous slide. It's on the order of, and actually a little bit larger than the annual CO2 savings from renewable technologies such as the solar PV and wind. And the reason of this, because of this, is the high annual capacity factor of CHP. You can see in the third row down that the industrial CHP capacity factor is about 90%. Utility PV, the national average is 24%. Utility wind is 34%. So CHP ends up generating a lot more power and thermal energy per megawatt of capacity installed, which results in, even though on a megawatt hour basis, the CO2 savings aren't as large as renewables such as solar or wind. On an annual basis, it ends up saving a considerable amount of CO2, again, comparable to what's some of the renewable resources on the grid are savings right now. And you can also see how CHP's savings further increase if that system was fueled by biogas or some other net zero fuel, as in the third column over from the left in this table. And this chart really, again, dives in a little bit more to show that CHP is more efficient than current marginal generation and can provide energy and CO2 savings. This chart compares the net electrical efficiency based on power output divided by fuel chargeable to power. And that means for CHP, there's a credit on the fuel going to chargeable to power based on the displaced boiler fuel that the thermal output would replace. And it's the electrical efficiency of typical CHP systems in the green bars to the left. You see the 20 megawatt gas turbine I just talked about, 8 megawatt gas turbine, and a large and a smaller recip engine there. And compared to the efficiency of new natural gas central station generation on the right. And I'm fumbling a little bit here because there's supposed to be some numbers on top of these bars here that show the marginal, or basically the net emissions factor in terms of pounds per megawatt hour for each of these technologies. And I won't go through them all, but that 20 megawatt gas turbine CHP system all the way to the left, the net CO2 emissions are 654 pounds per megawatt hour. For a natural gas combined cycle system, the gray bar, the second gray bar in from the right, which is sort of the state-of-the-art marginal gas generation that you would find right now. It's around 50% efficient, and the CO2 emissions in terms of pounds per megawatt hour are 792 pounds. So you can see there's some significant advantages in terms of emissions factor from the electricity produced from CHP compared to central station marginal generation. This means that natural gas CHP could meet those marginal grid requirements more efficiently and with less carbon emissions than central station resources today. And furthermore, the efficiency and emission advantages of using CHP as this marginal resource should remain as the natural gas infrastructure decarbonizes, or I should say, if the natural gas infrastructure decarbonizes, and renewable fuels such as RNG and hydrogen enter the market on either side of the meter. Another demonstration of this is that we included in our paper it takes a look at the while economy-wide electrification and decarbonization of electric generation is being pursued aggressively in many states and cities. Again, fossil fuels and natural gas specifically are likely to remain on the marginal generation as the marginal generation resource for the near and midterm, and may be necessary over the longer term in some regions to support the greater integration of renewable resources and provide grid regulation services. I think how much and whether these kind of combustion marginal resources will be natural gas or hydrogen or renewable natural gas, I think it certainly is in question, and we'll see where that goes. But a 2020 study completed by ICF for the Energy Solutions Center here in DC evaluated the regional emissions reduction potential of natural gas to CHP through 2050. The study used state-level economic forecasts and legislative emissions mandates, such as zero grid emissions in New York by 2040 and in California by 2045, to model marginal grid generation resources by region through 2050. And as shown here, natural gas fueled CHP continue to reduce carbon emissions compared to the marginal grid emissions in these regions, except for when you got to 2050 in New York and California, well beyond the typical lifetime of CHP systems in every region, again, outside of New York and California. So I personally, I don't think putting in natural gas CHP today is the road to a stranded asset. It will continue to save emissions for a long time, as long as natural gas is on the margin at the grid. And then hearkening back to what Richard was talking about, there is a path to no carbon CHP through hydrogen. And that really is this slide. So natural gas CHP can be a tool to produce significant CO2 reductions in the near to midterm. And the question does remain, what's the long-term role of CHP in decarbonization? Again, we think there is a key role moving forward, particularly in using low to no carbon fuels such as hydrogen to produce efficient, reliable energy services to markets and processes that don't lend themselves easily or cost effectively to electrification. The figure on the right is from an American Gas Association study that was done in 2019, looking at the resource base and the paths to low carbon fuel feedstocks, gaseous fuels that could be used in a pipeline system, and includes renewable natural gas, such as coming from food waste, animal manure coming from anaerobic digestion, thermal gasification of agriculture residue, energy crops, and power to gas either through green hydrogen or blue hydrogen from natural gas with carbon capture. And we feel that these are all paths to the use of CHP as a long-term solution to decarbonization. Current CHP projects routinely operate on biogas and hydrogen blends, and all major gas turbine engine manufacturers are introducing 100% hydrogen capability systems, many looking at 2030 as the point for commercial availability. We see, looking at existing packaged CHP systems that Almost all of them can operate on natural gas hydrogen mixtures of 5% up to 40%. The 40%, one example, 40% are engine systems from 2G Energy. They currently, the products they sell can operate up to 40% hydrogen natural gas mixtures. They are currently in development of 100% systems that can be field modified on these existing products. So we do see paths to 100% hydrogen capability from all the major manufacturers of gas turbines and engines. And again, we do see these renewable fueled CHP as the path to decarbonize thermal end users in applications that are difficult to electrify or decarbonize critical facilities that need dispatchable on-site power for long duration resilience. And we also see the high efficiency of CHP being able to extend the supply of what promised to be, at least initially, scarce and I think expensive alternative fuels. Just to go a little bit deeper, obviously, the question is how large is the potential resource base for RNG and hydrogen and these alternative fuels? I think work in this area is just starting to accelerate in the U.S. and there aren't a lot of specific estimates out there yet. But again, taking the American Gas Association work as a start from 2019, the study considered three scenarios: a low resource, a high resource, and an overall technical potential for renewable natural gas. Looking at the comparison here on the graph in the lower left-hand corner, the high resource scenario estimated a supply of around 4,500 trillion BTUs per year of RNG at a cost that was considered competitive with other carbon abatement options of between $55 and $300 a ton of CO2 emissions reductions. This 4,500 trillion BTU is in fact nearly 60% of current industrial natural gas demand of a little over 7,600 trillion BTU. So we do think there's a path to significant resource base of alternative fuels such as renewables and green hydrogen. And if you look out into the long-term future, probably even more potential for hydrogen. And just to support that, a World Resources Institute report released late last year compared the resource estimates for RNG from three different studies: the AGA study and some earlier studies from 2013 and 2018. And my read was that they all sort of hung together in terms of resource estimates that you could identify in 2035 or 2040. One of the things that we've tried to demonstrate is how natural gas CHP can decrease emissions in the short term when inefficient natural gas is on the grid margin, and then how increasing levels of renewable and low to no carbon fuels could maintain that emission advantage of CHP as the grid decarbonizes. So this is sort of our sort of crude attempt just to make that point. A typical natural gas CHP net CO2 emissions net CO2 emissions of 710 pounds per megawatt hour generated is this line here, which is just above 700 pounds per megawatt hour. The current average marginal emissions rate of national average for the grid is about 1,550 pounds per megawatt hour. And that's, again, from EPA's AVERT estimates, and that's the starting point up here. And if you just, for simplicity's sake, assume that by 2050, that grid is going to be decarbonized and goes down at a straight line to 2050. There's a lot of reductions that will happen on the grid before CHP is not, natural gas CHP is not providing any more savings compared to the grid. And once the grid emissions gets below that 710 pounds per megawatt hour, which is a natural gas CHP emission rate, The introduction of different levels of zero carbon fuels to the fuel mix for CHP can maintain that efficiency and emission advantages. And again, just shows that CHP can be an important part of the solution for the long term. And my final slide shows that being part of that is it can extend the supply of renewable and zero carbon fuels. Richard pointed out that there's a lot of potential uses for hydrogen or RNG. These fuels could be used directly in industrial boilers and heaters, or for generating carbon-free electricity at the grid to supply to industrials. However, again, the supply of RNG and hydrogen will likely be limited in the beginning, and there's a compelling case that the use of these fuels should be prioritized for high efficiency applications such as CHP. There are other applications as well. Using RNG and hydrogen on-site in on-site CHP to provide needed thermal energy and electricity would ensure that these fuels are used most efficiently. And again, this is sort of a crude example showing the impact of providing electricity and steam to an industrial site, either through combined heat and power that's using RNG or hydrogen, or a decarbonized grid and an electric boiler. And that decarbonized grid would be using RNG and hydrogen to generate the kilowatt hours going to the site. And again, just in this sort of crude comparison, you can see that CHP would provide those same energy services using 60% less renewable zero carbon fuel than getting those services, than electrifying everything at that site and providing carbon-free electricity to the site that's generated either through hydrogen or RNG at the central station. So we do think there's a good story for the use of these, good reason for the use of these fuels most efficiently as possible. And one efficiency path is certainly through CHP. So I'll end that with my contact information. To summarize, we do believe that in a deeply decarbonized economy, that CHP systems can still retain emissions and efficiency advantage through the use of low to zero carbon fuels. As industrial needs for heat and power evolve on this path to a low carbon future, I think the ways that CHP can support those needs will also evolve. The value provided by CHP will include reducing energy use and greenhouse gas emissions in the near term, while gas and coal is still on the margin. But it's also supporting fuel flexibility and efficiency over the longer term, providing low carbon energy reliability and resilience to critical infrastructure, and I think really serving as a flexible and efficient low to zero carbon resource for future industrial power and thermal needs. With that, I will turn it back to you, Perry.
All right, thanks, Bruce. You really did fill in a lot of gaps that I had on the role of CHP going forward. We've got time for just a few questions, and so I want to shoot this over to the panel. First, for Stefan, in the U.S., we see the small and mid-sized businesses and the industrial codes that they represent, typically assembly and electronics and so forth, actually stack up to include an awful lot of the greenhouse gas emissions. And they tend to be small, mid-sized businesses. What does your data suggest are kind of the best strategies for motivating those businesses to think about their options for low carbon fuel, low carbon technologies going forward, based on what you know about what motivates them?
Many thanks for that question. And indeed, the small and medium-sized companies are a crucial factor. As a matter of fact, if we look at the overall number of companies, they're over 99% of all companies, at least in Europe. And in contrast to the common perception, they are also the highest share of energy-intensive companies among the mid-cap companies. So it's not the large ones that are most energy intensive, it's on average the medium-sized ones. What can they do? That differs, as indicated, by their sector. typically there are so many savings that are very economic to be accomplished without lots of investments done in terms of energy efficiency, on-site things. But the critical issue, it's not their day-to-day business. So it's not on their mind. So the first component, which is really the game changer, is opening the eyes that they really have to take action for their own good very, very quickly before they are outrun. Why? Because the big OEMs, for instance, car manufacturers, now are increasingly jumping on the decarbonization train, requiring their products to be net zero at the point of handover. They hand that down through the supply chain and forcing their suppliers to be ready to jump immediately. However, if they're not prepared, they are screwed. And so efficiency measures on site, there are large potentials. There are many support schemes. However, it's the micro and small companies, at least in Europe, that are not planning to go for aids or subsidies simply because it's too complicated. So the findings indicate that they strive or they seek a sort of a caretaker, somebody that they can trust, and others that they can relate to jointly address the issue and move forward.
Okay, great. Rich, this issue of the relative density of hydrogen,
Right.
and either the need for 3 times the pipeline size or heavy compression has come up, and how truly competitive hydrogen might be. You mentioned also the possibility that this might be something that would happen within the context of starting with local clusters, industrial clusters. So can you talk a little bit about that idea?
Yeah, it shouldn't have to be 3 times the diameter because the cross section goes as a square of the diameter. So that's helpful. And in the consideration in the European hydrogen backbone, they are replacing the very small pipelines like 16 inches with 36 to 48 inches. Planning for them to be able to stay at lower pressure for a good amount of time, and then by the time they need to be pressurized higher, then the compression technologies would be better developed and less expensive. You're tying it in with the industrial clusters also goes along with Caleb's question about the Australian National Hydrogen Plan, which I had not actually looked at until Bruce started speaking, and then I quickly got myself up to speed on it. And that's pretty much an industrial cluster or hub model. And that is also what all our European colleagues tell us is really kind of how everyone's looking there. And we are thinking of it, on this side of the Atlantic as well. We've done a project for the California Energy Commission on industrial hydrogen research and development, and some of the recommendations could well be related to industrial clusters. It doesn't mean that those industrial clusters or hubs wouldn't also be able to serve, let's say, mobility fuel. Basically, whatever, if it helps in terms of scale to be able to also supply fuel for large vehicles. It could be like if you're at a port, some of the large barrage vehicles, there's like 40,000 of them at the port of LA that are constantly shuttling back and forth. And so there's a lot of possibility for integration of different uses and production technologies and so forth, and efficiencies in industrial clusters. And even some of the European Innovation Fund submissions, we're aware of one of them, Air Liquide, where they really proposed utilizing the oxygen for oxygen processes nearby, utilizing the heat for various high and low temperature processes, and the hydrogen as well. So integration within the industrial hub lets you utilize a lot and also better follow the renewable energy intermittency curve, because you can combine technologies that way.
All right, thanks, Rich. And then, Bruce, a couple of questions around the adoption of CHP, kind of starting with today's picture and current fossil fuel prices, and why hasn't CHP become more widely adopted across the entire market? And then kind of looking forward, I think these questions of will policy actions like the value of RECs and carbon pricing, perhaps, and the sort of the advancement of zero or net zero carbon policies. Does that really, in the end, does that favor CHP as a significant, having a significant role, particularly in industrial settings?
The first question about CHP adoption, I mean, CHP is a complicated project. There's a lot of interfaces that have to be done electrically and thermally with the site, interfaces that have to be done with the utility, and it's fairly complicated, and a lot more larger companies with technical resources are a lot more comfortable with it. Having said that, there are the appearance are now commercial package systems that have taken away a lot of the stick-built costs and uncertainty with CHP. And a good resource, if you just Google package CHP e-catalog, you'll find a resource from DOE that has, I think, 270 sort of vetted packages and CHP packages ranging from 24 kilowatts to 16 megawatts, provided by vetted packagers and solution providers that are trying to adopt that. So there's some efforts to try and make this less of a complicated, expensive, and difficult project to put CHP in. On the possibility of basically having CO2 benefits push the CHP market, I think we're all hoping that CHP can be recognized for its ability to save emissions and because of its efficiency. And I know, as an example, I talked a little bit about RNG. There are, I think, some experiments going on in California where, like, a facility can now buy renewable power from anywhere, even though it's generated far away. I believe it's the University of California, San Diego campus that is buying directed RNG for its CHP system. That I think would serve to offset its Scope 1 emissions in that case. So I think there are experiments going on and approaches going on as RNG, and I think as hydrogen gets into the mix, that should be a big help for CHP. Also, I think with everything going on, the price of power is going to go up, and again, to the extent there are fuels available that can be used to generate power on site, that could, a little bit more cost effectively, that could have a big impact.
Sure. Well, I think your last diagram, as you showed the declining line kind of striking through various time frames where fossil fuels sort of become in disfavor and pricing of power and so forth, renewables, come down and emerging into that time frame when we have renewably generated alternate fuels. It's very interesting to see how that continues to, CHP can continue to play a role in extending the value of those renewable resources. And I think it's a very important point that we need to think through as we strategize for sort of the overall energy structure supporting the industrial and heavy commercial economy going forward. So thank you for that. Well, that's all that we have time for today. And so thanks everyone for your time. Thank you to the panel. Again, a reminder, we have another session this evening where folks will be available to take more questions and just discuss in general thoughts about what you've heard today. So we really appreciate our panelists' time today and your insights, and thank everyone for your attention and participation. Thanks again, and have a great rest of your afternoon.